So, good morning. Last week we have found that there is something, some strange thing called electromagnetic wave that comes out as a solution of Maxwell equations. We have derived the wave equation and then we have found that it's quite complex, and we have simplified it for a 1D case of a plane wave propagating in the z direction, and we have also simplified that for a harmonic wave so that we can use phasors, and then we had the solution, and that's the point from which we would start now. So we have had the electromagnetic wave equation Laplace applied on, for example, E, now it's a vector and phasor, plus a square of the wave number E, vector phasor, and that is in the area where there are no sources equivalent to 0. So this is the simplest formulation of the wave equation for phasors. Now we have got for 1D case the solution for a propagating wave, which came out like E vector phasor as a function of the coordinate z is equivalent to E vector phasor 0, that is the phasor of the electric field strength at the beginning of coordinate z, times an exponential e raised to minus j k z. And that is the point we have arrived to. Then we have a little bit talked about conductors and non-conductors, that is dielectrics. And now I would like to raise another question. In so far we had an equation, a wave equation, which governs electric field strength. By multiplying this equation and therefore the solution by the permittivity, we could get the same formulation for D, electric flux density. By multiplying the same equation by conductivity, we can get this for current density. And if we had started the derivation from Maxwell equations from the other end, we could have the same pair of equations identically looking for magnetic flux density and magnetic field intensity. So we now somehow have 5 equations, and there must be a question, are they somehow connected? Well, possibly we can see that if we multiply this equation by epsilon or multiply it by sigma, the specific conductivity, then in fact that's only one independent equation. But then there are the 2 equations for magnetic flux density and magnetic field strength, and there is a problem. Are they independent, or is that something that is connected to the same phenomena? And this question should be replied. That's an important question. So let us consider now, for example, a Maxwell equation that on the left side has a circulation of electric field strength. And as you remember, this is minus dB over dt. Now, we should have to decorate this a little bit. In order to obtain the result of this, we use a kind of a symbolic determinant. So to carry out this mathematical formulation, we would possibly do something like the unity vector in x, y, and z. I'm using Cartesian coordinates because we have used Cartesian coordinates for developing that wave equation. So we stay in the same coordinate system, so it's relevant. Now, this means that we have in the first row the elements that we got out of the nabla operator, which is the first derivative against x, the first derivative against y, and the first derivative against z. And in the second row, we got the components of the vector. So that would be e, x, e, y, and e, z. So this is a decryption of this formula, of this left-hand side. So I could put here, it's equivalent to minus dB over dt. But now let us consider that we have a wave, and let's say, okay, so let's have there a component. Let's orient our coordinate system. We have first oriented it so that it pointed to the direction of propagation by its axis z. So let us now orient the electric field strength so that it points to the x direction. If it points to the x direction, then it means that it has not any y nor z component. So if it points to the x direction, we can neglect those two. So then this is 0 and this is 0. For this simplified case, we can do that. And now we can carry out the calculus of this determinant. So what components would that have? First, we have the hiding rule. There would be no component in the x direction because that is 0, there is 0. So there is a 0x. So let's put it down. So the result is 0 in the direction of x. Can you read the blue pen, please?
Yes.
Okay, so I will. It's better to use colored pens, but not always they are readable. Okay, so there is no component in the x direction. So let's go on. What about the y direction? What in the y direction? So let's hide those two, the row and the column. And in the y direction, there would be derivative of ex against z and the derivative of ez against x. Now, we have been hiding the second component on this line, so the sign is minus. So the result is minus derivative of 0 against x, which is 0, minus derivative of ex against z. Okay, so there might be some component which would be plus a derivative of ex against z. Good. And let us go on. Now we would try to find the z component of that wave. So we will hide this column and row. It is the third. So we have changed from plus to minus to plus. So there will be plus. And what we can have here is a derivative of 0 against x, which is 0, plus a derivative of ex against y. Okay, so we would have, sorry, I have to put there also the direction. And now we have a component which I will again mark in blue, and that is a derivative of 0 against x, which is 0, minus a derivative of ex against y. And that is multiplied, that belongs to the direction of the unity vector in the z coordinate. But now, look, we have started to examine a plane wave. And a plane wave was defined in the manner that its components only depend on the z coordinate. So we have a non-zero ex component, but it's constant when you move around the y-axis. So this is again 0. So we have found out that the whole determinant has only one non-vanishing component, and that is, again, that has the direction in the y vector or y-axis, and the magnitude is a derivative of ex against z. Now this is important, and we shall continue with it. Just, we should have written here the right side of the equation. And now I will write it properly to a new line. So our new equation we have obtained is the following one. It's a derivative, a partial derivative of ex against z, and now it can only be dependent on the y component of the right side. So what we can write here now is that this is minus a derivative of by against time. Now we have used vector algebra, but now we have only a scalar equation that it connects an ex and by component. Now this would be difficult to go on for arbitrary time dependence. But we could go on quite easily if we remember that our original equation has been prepared for phasors. So yes, if we make these phasors, we arrived to something which we can handle easily. First, remember, this is a derivative of ex against z, but we know the z dependence, so we can carry out the derivative. Now, this is a phasor, and you know that deriving phasors against time is very simple. It is just a multiplication by j omega. Well, that would be simple. So let's carry out both derivatives. On the right side, we have minus j omega b y. That's it. Now let's go to the left-hand side. We have the ex against the z. So we have to derive a function which is an exponential. So in a similar manner, we would carry out the derivative like multiplication by minus jk. Okay, so we have minus jk Ex phasor is equivalent to minus j omega b y. And this is an important conclusion. We started with an electromagnetic wave that has been propagating in z direction. Now, we have found that this wave has two components that are not independent, because we can find out that there is a direct equation which establishes the ratio between Ex and By. And this can then be used to connect electric and magnetic field of the wave. Not only that, we found out that for a plane wave propagating in an isotropic, homogeneous, stationary, linear media, those two components must be perpendicular. So you have the electric field pointing, for example, up in the x direction. You have the magnetic field pointing in the y direction. And the whole result is propagating to the z direction. By the way, do you remember Poynting's vector? The transmission of energy is obtained by multiplying E times H in a vector sense, and the result points to the direction of propagation. So we had started with a wave that should propagate in the z direction. We have found two components of the wave, and it makes sense. The direction of propagation of power or energy is really the z-axis, so it's correct. This could work. It's physically sound. So we have found this. Now, let us make a small change. It is more used that people use magnetic field intensity H than magnetic field flux density B. And we can convert that quite easily into the form that the right side is minus j omega mu h in the y direction. Sorry, this is not a vector, this is only a phasor. But now what we can do to make it absolutely clear, we can describe the ratio between electric field strength and magnetic field intensity in a closed form. So let us do that. We divide the equation by magnetic field intensity Hy and divide the equation by minus jk. And what we will obtain is Ex phasor divided by Hy phasor would be j omega minus j omega mu divided by minus j k, and that's it. So first we can cancel out minus, then we can cancel out j, and we have an expression that tells that there is a fixed amount, a fixed ratio for a wave, plane wave propagating in the z direction. There is a fixed ratio between the Ex and Hy component. To read it better, we have selected one of the axes to point in the direction of the E field, so we can also tell there are two perpendicular components and the ratio of those two components is fixed. And it is omega mu over k, which could be also rearranged as a square root of j omega mu over J omega epsilon plus sigma, where mu is the permeability, epsilon is the permittivity, and sigma is the specific conductivity of the material. So now we have found something which is a quantity that somehow governs the electromagnetic wave, and this quantity has a special name. It is called free space or wave impedance, and it has a special letter, ni. So this is a special quantity. When there is a special quantity, we should possibly find out its value for some general case. So the most general case or most common case for wave propagation is free space vacuum. And the second one is the air, which is not very different. So what would be the value of the impedance for vacuum for free space? Let's get it. So if we put here the quantities for vacuum, we would get a special ratio. I will try to get a red pencil. So, is it readable?
Yep.
So this would be the ratio between the free space permeability and the free space permittivity, because there is no conductivity within vacuum. And this ratio is more or less equivalent to 120 pi ohms, which approximately is 377 ohms. So this is an important value of the free space impedance. And now we know that although we can formulate the wave equation for 5 distinct quantities, that is electric field strength, electric field flux density, current density, magnetic flux density, and magnetic intensity. In fact, we have only one free element, and that is any of them, because we can then convert the result into any of those values. So, first important point, electric field and magnetic field are perpendicular in a plane wave. They are not independent. They are governed or bound by the free space impedance, which has a fixed value for vacuum and of course could be calculated using this equation for other media. So this is an important point. We have discovered that there is a plane wave which has a fixed ratio between its components. Now I will make a short point that is also interesting. And this point is about the phase of those two phasors. So first let us have the wave propagating through non-conductive media like dielectrics, like vacuum. Then the impedance is a real number. So the ratio of two phasors, that is a real number, in fact means that both phasors must be in phase. There is no phase shift between electric and magnetic field. This is propagation within dielectrics. Just if there is any conductivity. And you remember from last lecture, that means there are losses. So once those losses come into action, there would be some attenuation, and at the same time, the electric and magnetic field would not be in phase. For example, the magnetic field will be a little bit retarded. It will fall behind the electric field phasor. And given a propagation in a conductor, then we would find out that there is negligible displacement current. We would have this completely imaginary. If we make a square root of a completely imaginary number, we would get a phase shift between electric and magnetic field, which is exactly 45 degrees, or pi divided by 4. And that is the phase shift for propagation of an electromagnetic wave inside conductor. Well, we will see that there is not much propagation of an electromagnetic wave inside a conductor, but if there was any, it would have a phase shift of 45 degrees. Now we have derived some important conclusions, and I would like to get your questions if there are any.
One question, you say that the phase shift would be 45 degrees. Would be always like this?
Well, if in the case that you can neglect displacement current against real current, against conduction current, which is the case we call a conductor, in that case it would be 45 degrees. But you know, then we have the number of other media, like for example human body, which is for most frequencies of electromagnetic wave a kind of lossy media. It's not a dielectrics, so the phase shift is not 0. It's not a good conductor, so the phase shift is not 45. It's something in between.
I see. Yeah, thank you.
So if I may, I would make a 5 minutes break, then you can again ask questions, then I will turn my paper sheets and we will go on to another topic with electromagnetic wave. See you in 5 minutes.